Now, something that I'd like to point out here is that if we only take the subgroup of rotations, okay, um, and those transformations essentially look, let's say what we'd written down earlier, look something like this. Okay, there is some kind of transformation matrix here. Let me just write it down. So this is a rotation in the xy plane. Would look like this. So this is a rotation in the xy plane by an angle theta. And you can see that all these rotations do not mix the time coordinate with the spatial coordinates. So essentially, other rotations would only involve this 3x3 block over here. Okay. And so therefore, all my rotation matrices, my 4D rotation matrices, can be written in the form where I think of lambda as some matrix, which is a 4x4 matrix, but then I have some 3x3 sub matrix, which is the rotation matrices. And these rotation matrices depend on the angle or axis of rotation, and they depend on both the angle as well as the axis of rotation. And these matrices R satisfy the property that R transpose R, where these are 3x3 matrices, is the 3x3 identity matrix. Okay, this just comes from the fact, I can stick in an identity matrix here. This just comes from the fact that G itself has an identity matrix sitting in the bottom lower diagonal, lower block, 3x3 block. Okay, so the matrices are which if I just take these 3x3 matrices which satisfy this equation, these satisfy the equation R transpose R is identity, and these are 3x3 matrices. So these belong to the group of what are called O3. Okay. Orthogonal 3x3 matrices is the rotation group in 3 dimensions. And again, this group also includes the parity operation. It includes the operation of this, which is a flip of all my spatial axes. So if I want to remove, this is the 3D parity operation. If I want to remove this parity operation, I would impose an additional restriction that my group is SO3. That is, the determinant of these matrices R is +1 and not -1. So if determinant of R is +1, this gives me what are called proper rotations. Okay. There's no way to talk about orthochronous because orthochronous refers to time, and that would refer to the Lorentz group of transformations. It has nothing to do with rotations. So proper rotations is the group SO3. And if we want to generate things like mirror flips, that is, imagine an operation like this. This takes us from an observer with axes x, y, z to an axis where x, so this is an observer S, and then there's an observer S prime with axis x, y, z, where only the x-axis is fixed. So this is like looking at a mirror in the YZ plane, right? And then you flip your axis about this mirror. So such an operation, okay, can be generated by a combination of a rotation plus the parity operation. Okay, that is, you imagine first that you do a parity operation. So the parity operation brings you to x, y, z, and you follow this by a rotation about the x-axis, okay, by 180 degrees. And what that would do is it would bring you to x, y, and your z-axis would be up here. Okay, so this would be a parity operation plus rotation about the x-axis, or rotation in the yz plane by 180 degrees, okay, would achieve something like this. Okay, so this mirror flip in uh, the yz plane, that is, if you imagine a mirror sitting in the yz plane at x is equal to 0, okay, that operation can be achieved by a combination of the parity operation and a rotation operation. Okay, and if we restrict ourselves only to pure proper rotations, that is without parity transformations, even these mirror flips are forbidden. Okay, because you can see that the mirror flip also involves a left-handed coordinate system. X cross y is not going to be z, but rather is going to be in the minus z direction.